looking at torque. So I start off with the question, what causes a change in an object's motion? And you guys know this from before. It's a force. It causes a change in an object's motion. It causes a change in an object's rotational motion. That is a torque. So torque is the rotational analog, the rotational equivalent of force. Now if I've got a tennis ball or any other object that can spin, that can rotate, what would I do to spin it? Well, I might do something like this, right? What I'm doing is I'm applying force, but in a particular location on the tennis ball. So, I need to apply force. So, force causes torque. And it's pretty intuitive that if I push harder, it'll spin faster. So, greater force, maybe I shouldn't put an arrow here. Greater force leads to greater torque. Obviously, on a video, you can't see what I'm talking about with the door pushing contest, so we'll have to skip out on that for a moment. But you guys, know where door handles are located. A door handle is never placed right next to the hinge. It's placed on the opposite side of the door, right? If it was placed right next to the hinge, it would be harder to open the door. So the point that I'm getting across there is that distance matters. Distance from what's called the axis of rotation matters. The variable we use for that is r, and the farther away you are from the axis of rotation, the easier it is to cause an object to rotate. And think about what direction works best. Well, if you take a door, let me draw for a moment. Say this is your hinge and you've got your door, and you push this way on the end of the door, it's not going to rotate, right? You need to push this way or this way. And this is, pointing straight at the hinge. This is making an angle that is 90 degrees. If you push at some angle in between, it's going to be less efficient. So angle matters, and closer to 90 degrees yields greater torque. And it turns out the relationship between force and torque is linear. Torque, the variable, is the Greek letter tau, which is just a T with a curvy top. Turns out the force and the radius, they're proportional to the torque. And then if you have something that's maximum at 90 degrees and 0 at 0 degrees, that sounds like a sine function. So this is our formula for torque. The unit torque, well, you've got force times radius, so Newton times meter, which is a bit odd because a Newton meter is also equivalent to a joule. This is not a joule, but a Newton meter is a joule, but the difference is that energy is a scalar and torque is a vector. So that's how we distinguish them, and the direction of that is determined by the right-hand rule. So if I have a door that I'm rotating and I push it this way, well, this force would cause the object to rotate that way. So then according to the right-hand rule, the torque caused by that force would be coming toward the screen out of the page. That's how we determine the direction. Forces add. You guys know the net force on an object causes an acceleration. That's Newton's second law. It is also true that torques add in the same vector-like way, and the net torque on an object causes, as you might expect, angular acceleration. So force causes acceleration, torque causes angular acceleration. Here's an example of there's a door, length L, hinge on one side. It's helpful to draw a picture for these, and actually on the AP exam, you'll often be asked to draw pictures for things involving torque, and you need to put the forces at the correct location. When we were drawing force diagrams, doing Newton's second law things for linear stuff, we were treating our objects as point masses. We didn't really talk much about it, but we were treating them as point masses, so all the forces sort of just acted at a single location. But with torque, location matters, so you need to make sure you not only draw the correct arrow in the correct direction, but also originating at the correct point on the object. So we've got a door length L, hinge on one side. Person A exerts a force F perpendicular to the door at a distance L over 2 from the hinge. So when viewed from the top, person A pushes clockwise, so clockwise would be that way. So person A exerts a force F, a distance of L over 2 from the hinge. Person B exerts a force F over 3, a distance L from the hinge, at an angle of 30 degrees to the door. And they're pushing in opposite directions, so we've got F over 3, 30 degrees all the way at the end. And they push on the opposite sides of the door, yep. So taking up to be the plus Z direction, find the net torque on the door. So this is a top view of the door, so up would be out of the page, down would be into the page. So to find the net torque, we just add up the torques. So we're adding up FR sine theta for each value. So for this one, well, that torque is going into the page, so that's going to be which is representative of down, so that's going to be negative F times L over 2 times sine of 90, which is 1. If forces are perpendicular, you can just drop the trig function. And then we have a torque in the positive Z direction, force of F over 3, distance of L, at an angle of 30 degrees to the door. And so we can work this out. This is, of course, minus 1/2 FL plus, we know sine of 30 is 1/2, so 1/2 times a third gets us 1/6. FL minus 1/2 plus 1/6 is minus 1/3 FL, or 1/3 FL in the minus Z direction, aka down. Yeah. So we can add up torques and calculate them. Right. Now, you guys know the proportionality between force and acceleration is mass. Moment of inertia is the rotational equivalent of mass. Obviously, again, we're going to skip the demo because you can't really see. This is something you would need to feel, and we can't really feel that. So, for a point particle moving in a circular path, Newton's second law just says net force equals ma. Okay, and if we multiply both sides by r, well, this is going to be torque. We'll assume for the moment that our forces are tangential to the circular path, so the r is the radius vector is perpendicular to the force, so we have a sine of 90 degrees. So then that left side becomes net torque, and the right side becomes m/r, and we know tangential acceleration. We're talking about tangential stuff. Tangential acceleration is equal to r alpha, so we have m/r alpha times r. And so that gives us that net torque is mr squared alpha. This mr squared is the moment of inertia of a point particle. So the rotational version of Newton's second law says net torque equals I alpha. Moment of inertia is I. And yeah, for a point particle, the moment of inertia is mr squared. The unit for that is, you just figure it out. Mass is kilograms, radius meters squared. So you can think of any object as a collection of point particles whose moments of inertia. So if you have a continuous object, you just add up mr squared for each little point, and when you add up an infinite number of those little mr squareds, and when you do that, that's an integral, and we're gonna do those integrals, some of those integrals next class. Concept-wise, you can think of, okay, mr squared. So moment of inertia is determined both by mass. So an object with bigger mass is moment of inertia. But then this r squared also tells you that the farther the mass is from the axis of rotation, on average, the greater the moment of inertia is going to be. So you can use that to make some qualitative judgments about which object will have a greater moment of inertia.